Good evening, friends. So, in the last lecture, we have seen about the crystal structure. Now, the furthermost part of this particular topic, that is the structures of material. The crystal structure, what is the crystal structure, what is the unit cell, what is the lattice cell, that particular basics are very much important just to calculate the number of units per unit cell as well as the atomic factor, that is, or we can say the atomic packing factor for the further calculations. So today in this particular lecture we are going to cover the average number of atoms per unit cell. So according to the structure, in the last lecture we have seen about the structure. So basically 14 Breves lattice structures are there, and those structures are just having some sort of that shapes. So according to that particular shapes, or that we can say that structure, how the average number of atoms per unit cell has been calculated, that particular part we will cover in this particular lecture. So first of all, the cubic structure, it is there. So how that formulation has been carried out to calculate the average number of atoms per unit cell. Here the explanation, it will be there. You just try to understand how this formula has been generated over here. This is the formula for calculation of number of atoms per unit cell. Okay, so what is the unit cell? That we have also covered in that particular last lecture. The unit cell, basically it is just a combination or addition of lattice and bases. Okay, so the corner atoms are shared by the 8 cell in the cubic structure, 4 above and 4 below. So whatever may be the corner atom of this particular atom, okay, or corner atoms. So these corner atoms are shared by the 8 corners. So this is 1, 2, 3, 4, 5, 6, 7, and here will be the eighth corner. Okay, so these are the corners. Here you can be able to see. So these particular atoms are shared by the 8 corners. So this 8 atoms, okay, so 4 below and 4 above. So the atoms are shared by the 8 cells. So this is one particular atom and it is shared by the 8 cells. So this is related to the corner atoms. Then face atoms are shared by the adjacent two cells. So if it is the face atom, it is shared by the adjacent two faces. This is the 1 and 2. These are the adjacent faces and it has been shared with the adjacent face. So atoms in the interior are shared by only one cell. If the atom is included in the interior cell, so it will be only shared by any one cell. So that's why, just to calculate the number of or average number of atoms per unit cell, this will be the formula. So NAV is equal to Ne divided by 8. Now what is this Ne, NF, Ni? This has been explained in this particular slide. Okay, so NAV in the sense average number of atoms per unit cell. You just note down all those things. Ne is nothing but the total number of corner atoms in a unit cell. This is related to any factor. It is related to the corner number of atoms to the corner cell. Then NF you can be able to use here, that is the NC also. The term will be NC also. Then NF total number of face atoms in a unit cell, and Ni center of interior atoms. Okay, center or interior atoms. So why this is 8, why this is 2, or why this is 1, you just try to understand. NAV is equal to Ne, that is Ne is nothing but the number of atoms at the corner, divided by 8. Why this 8 come? Because this particular atom is shared by the 8 corners, 1, 2, 3, 4, 5, 6, 7, 8, or you may say 8 cells. So that's why this 8 term has been there. Then NF plus NF, it is nothing but the number of atoms at the face. Okay, so it has been shared by the two adjacent cells. So that's why this two particular term has been came over here. So this is shared by the two adjacent cells. Then Ni, that is the interior or center or interior atoms. Then this will be the N atom. So it is shared by the only one cell. So this one term will be came over here. So this will be a general formulation to calculate the number of or average number of atoms per unit cell for any cubic structure. So first of all, we will go with the simple cubic structure. So these are the atoms. Here you can be able to see. And after taking this cube as a separate one, here you can be able to see this lattice point, particular lattice points. So friends, in the simple cubic structure, in this particular structure, there are 8 atoms corresponding to the 8 corners. So here you can be able to see 1, 2, 3, this is 4, 5, 6, 7, and here will be the 8th. So these 8 particular atoms corresponding to the 8 corners, 1, 2, 3, 4, 5, 6, 7, and here will be a 8th corner. So, and there is no atoms on the face. So for the simple cubic structure, on the face there is no any atom. And also for the interior part, okay, there will be no any unit cell. So here when we will go for the calculation, the number of atoms at the corner, it will be 8. Then number of atoms at face, there will be no any atom on the face, so this term will be 0. Then number of atoms at interior, this term will be also 0 because there is no any atom at the inside. So when we want to calculate the average number of atoms per unit cell, this will, that particular formula here, it has been mentioned in this particular formula. NaV is equal to Ne by 8. This 8, 2 and 1, this term will be constant, so there is no any need to change those terms, but this term maybe gets varied, that is Ne, Nf and Ni. So Ne is the number of atoms, okay, total number of corner atoms in a unit cell. Then Nf, total number of face atoms in a unit cell, and Ni, center or interior atoms. So here the number of atoms at the corner are 8, so this 8 term will be there. Then on the face there is no any atom, so this will be a 0. Then Ni, that is center or interior atom, again it is no any interior or center atom, so it will be a 0. So this term we have taken as a 0. So when you want to calculate the average number of atom per unit cell, this will be a 1. So here you can be able to see NaV is equal to 1. Then the next structure is body-centered cubic structure. So in the last part or last lecture, that is in the Bravais lattice, that you have seen how that body-centered cubic structure, it is also called as a BCC in short term, BCC structure. So in the BCC structure, here you can be able to see this is this particular structure, how that BCC structure is there. What is the difference in between simple cubic and body centered cubic? This will be a simple cubic structure and this is the body centered cubic structure. So only one difference it is there. Along with this particular corner atoms, there is one centered atom, it is there, interior one atom. Here you can be able to see, okay, this will be a one interior atom, it is there. So how the calculation is carried out for average number of atoms per unit cell, here we will see. So in this particular structure, 8 atoms corresponding to the 8 corners are there. Like previous structure, that is the simple cubic structure, there are 8 atoms are there on the corners. So this is shared by the 8 corners. These 8 atoms are shared by the 8 corners. Then no atoms on the face. On the faces, these are the faces. So on the faces there is no any atom. Okay, but at the interior one atom is, it is included at the interior. So what are these terms? Ne is equal to 8, Nf is equal to 0, Ne that is the corner atoms. So these are again 8, 1, 2, 3, 4, 5, 6, 7 and 8. On faces there is no any atom, so this term again remains 0. But at the interior in this particular structure, one atom it is there, so this Ni is equal to 1. So again the calculation, that is for the average number of atoms per unit cell, NaV is equal to 8 upon 8, because this will be, this Ne term will be 8 over here, so this is 8 upon 8 plus Nf, that is on the face there is no any atom, so this will be a 0, 0 by 2 plus again at the interior one atom it is there, 1 by 1. So finally we are getting NaV is equal to 2. So in the previous structure NaV is equal to 1. So for the simple cubic structure, the average number of atoms per unit cell are 1. In the body-centered cubic structure, the average number of atoms per unit cell are 2, because this centered or interior one unit cell is added in this particular structure. Okay, might be these terms are now very clear to you, or you may calculate the average number of atoms per unit cell for the remaining structures also. So here now the next structure, that is the face-centered cubic structure, that is called as an FCC. So this diagram, it is their face-centered cubic structure. So might be, I hope you are getting very clear how that is the face-centered cubic structure in this particular diagram. Or again there is one more diagram, or we can say that animation it is there, how that atoms are there. So on the corner the blue color it indicates the corner atoms, okay, on the blue color, sky blue color, and the dark blue color indicates that atoms are indicates the atoms on the faces. Okay, so basically how many faces are there for any cube? Maximum faces for any cube. So 1, this will be at 1, this will be at 2, then at this back side of this particular face, third, and back side of this particular face, fourth, this will be a top face, 5, and at the bottom 6. So total number of faces for any cube, that is these are the 6 faces. Once again I will explain which are those 6 faces. This will be a one face, okay, which is indicated by the red corners. So this will be a one face. Then this is the second in that R direction. This will be a second face. Back to this front face, that is the back face, third one. Then back to this face, one more face, that is the fourth face. Then this will be a top face, that is fifth face, and at the bottom, opposite to this, at the bottom there is one more face. So 6 faces are there. So in this particular structure, the 8 atoms corresponding to the 8 corners. Similarly for simple cubic structure, that corner atoms are 8 over there, and again for the face centered, 6 atoms on the faces. So on the faces here we can be able to see 6 atoms are there, 1, 2, 3, and opposite to this, that is at the bottom 5, fourth, then back to this fifth, and back to this particular face, that is the sixth. So in this animation it is cleared 1, 2, 3, 4, 5 and 6. So at the corners 4, and these are the 4, 8 atoms at the corner, and at the center here you can be able to see the 6 balls at the on the faces. Okay, so these balls are nothing but the atoms. Okay, so how the calculations are carried out, here we will see now. Ne is equal to 8 over here, Nf is equal to 6, that is Ne is the corner atoms. So on the corner 8 atoms are there, on the face 6 atoms are there, but at the interior there is no any atom. Okay, so no atoms in the interior of the unit cell, so Ni term will be 0 for this. So on the face centered cubic structure, the total number of atoms we will calculate, that is NaV is equal to 8 upon 8. It is again calculated as per the standard formalization. So it will be 8 upon 8 plus 6 by 2 plus 0 upon 1. So 6, it is the number of atoms on the faces. This 8 term will be the number of atoms at the corners. So after the calculation, the average number of atoms per unit cell will be 4, because 8 upon 8 is 1 plus 6 upon 2 is 3. So 3 plus 1 is 4. So total average number of atoms per unit cell are 4 for the FCC, that is the face centered cubic structure. So again, from this particular diagram you can be able to see this is the atom of one atom. It is 1/8 part of one atom. So when you are in adding all those atoms 1 2 3 4 and bottom 4, you will get the one atom, and on the faces only half atoms are there. Okay, so here you can be able to see these are the half atoms, because this particular circle it is cutted as a half. So this is half, then bottom to this half it will be a 1, so this will be half, again below this will be half, so this is the second, then this will be a third, and back to this, means it is this 2 and half, and back to this it is 3. So for face centered cubic structure, the total or average number of atoms per unit cell are 4. Now next structure, that is hexagonally closed packed structure, that is HCP structure. Now in case of hexagonal closed packed structure, the formulation is somewhat different, because for the cubic structure only 4 corners are there, but for the hexagon total 6 corners are there. Here you can be able to see 1 2 3 4 5 6. For above face 6 corners, and for bottom face total 6 corners. Okay, so the total corners atoms are shared by the 6 cells. So any atom is shared by the, these are the 6 cells. So the formulation is slightly changed. Any divided by 6 in the cubic structure, this term instead of 6 it was 8, because that 8 corners are there. Now again for the face atom, again it is similarly the face atom, it is divided or shared by the 2 adjacent cells. Then the interior is shared by the 1 cell. Okay, so interior part, again when any interior part that is shared by the only 1 cell, the face atoms are shared by the 2 adjacent cells. 2 adjacent cells in the sense, just see in the FCC structure, the face atom it is shared by the 2 adjacent cells, because half it is over here and half is shared by the another cell. Okay, so this term might be clear now. The only slight change in the formula, that will be NAV is equal to NE upon 6. Only this particular term is changed. Instead of 8, the 6 it is there, because in the cubic structure 8 corners are there, and for the hexagonal it will be a 6 corners. Okay, because that atom is shared by the 6 corners, that's why. And in the previous, one more might be, there will be a confusion in you, because in the cubic structure we have considered all the 8 faces. Just see over here, 1 2 3 4 5 6 7 8 likewise. But here this particular atom, it is 1/8 term, means all 8 corners has been shared, but here in hexagonal only 6 corners we have considered, because this particular atom, means here 6 plus 6 12, don't take this term as a 12, it is only a sixth. Okay, why it is 6? Because 6 cells are there, 3 below and 3 above. So this particular atom is shared by half over here, half over here. That's why only the 6 corners has been considered, 3 above and 3 bottom. Now that's why how that formulation is there for the hexagonally closed packed structure might be, it is cleared. Now we will see for hexagonally closed packed structure how the structure it is there. Now in this particular structure there are 12 corner atoms. So on the each corner there is one atom. So 12 corner atoms are there. Okay, then 2 atoms on the faces. On the faces here you can be able to see these 2 atoms. Okay, so this is one and this is second. So on the faces, on this particular face one atom is there, on this particular face one more atom is there. So these are the 2 face atoms are there. Then 3 atoms in the interior of the unit cell. So at the interior side 1 2 and 3 atoms are there, which is shown by this particular color. Okay, 1, 2 and 3. Slightly yellowish color is there. So 1, 2 and these 3 atoms are there. So the any, that is number of atoms at the corner, 12. 6 above, 6 below. So 12 atoms. On the faces, 2 atoms are there. And at the interior, 3 atoms. 1, 2 and 3 atoms are there. So 12 upon 6 plus 2 upon 2 plus 3 upon 1. So we are just putting all those terms in that particular formula, that previous formula. This will be, this is the formula, Na upon 6 plus Na upon 2 plus Na upon 1. So here Ne, that is 12, 12 upon 6 plus 2 upon 2 plus 3 upon 1. So NaB, that is the average number of atoms per unit cell. This is 6. Okay. So I think all these things right now very clear, how to calculate the average number of atoms per unit cell. So four structures, or we can say the four important structure we have covered, that is the simple cubic structure. Okay, then BCC, that is body centered cubic structure, then FCC, face centered cubic structure, and last one is the hexagonally closed pack structure. So I hope now you can be able to calculate the average number of atoms, okay, for any structure. So might be in the examination also these structures may be asked. So thank you very much for today's lecture. We have just covered how to calculate the average number of atoms per unit cell. In the next lecture we will just go with the packing factor, how to calculate the average packing factor.